This is the second video of 3 looking at the topic of roots of polynomials. The first video looks at cases where we can just make a simple substitution to get a new equation with roots related to alpha, beta, and gamma, or alpha and beta in a quadratic case. This video is going to look at cases where we don't have a nice linear transformation to make, and we're going to have to make use of what are known as Vieta's relations, or you might have just seen referred to as algebra of roots before. So I'll do a quick intro looking at what those relationships are, and then a couple of examples looking at how we can use them. So starting off with the quadratic case, let's imagine we have a quadratic equation with roots alpha and beta. If that's the case, we can write it as alpha subtract beta times alpha x subtract alpha times x subtract beta equals 0. I'm going to generalize that a bit more by just saying could have a times that, and it would still have roots alpha and beta. Now, if we were to go and expand this, we'd get a lots of x squared. Plus, actually, I'm going to write a subtract there rather than have a subtract in brackets. We're going to have subtract a lot, and then we'd have alpha x and beta x. So I'm going to factorize that out and say we'd have a lot of alpha plus beta x. And then finally, plus a lot of alpha beta equals 0. What this means is if we have an equation which is in the form ax squared plus bx plus c equals 0, and we want to think about what the roots of that are, by comparing our coefficients, we're going to get, well, we've got the same number x squared, so that's all fine, but we're going to need that negative a brackets alpha plus beta is equal to b to get the coefficients of x the same. And we're also going to need that a times alpha beta is equal to c. Rather than stating the relationships like this, they're most commonly written as the sum of the roots, alpha plus beta, is equal to negative b over a by dividing by negative a, and the product of the roots, alpha beta, is equal to c over a. So these are two important results. You don't get given them in the formula booklet, so you need to know them off by heart. You need to be able to derive them very quickly indeed. Now, that's for the quadratic case. You do need to know for the cubic case and the quarter case. Once we've done the cubic case, I think the quarter case will become a bit obvious. So I won't go into that too much, but we will look at the cubic case here because that will see how this is going to go in a more complicated situation. So let's repeat the trick and say we've got a cubic equation with roots alpha, beta, and gamma because we're going to need the third root now. So if we do that, we're going to have a brackets x subtract alpha, x subtract beta, sorry, I've just lost my pen there, x subtract beta, and x subtract, and that letter there is gamma, equals 0. I'm not going to go through the whole expansion, but if you expand this, and you're careful doing so, you're going to get ax cubed. The x squared terms, you're going to get negative a brackets, and you'll have alpha lots of x squared, beta lots of x squared, and gamma lots of x squared. So factorizing that out, we can write all that. Then the terms with just an x in are going to be a lot of alpha beta plus beta gamma plus gamma alpha x. And finally, the last bit is just going to be subtract a alpha beta gamma equal to 0. So we're going to compare in the same way we did with the quadratic. Let's imagine that we're looking at a quadratic equation presented in the form ax cubed plus bx squared plus cx plus d equals 0, and compare our coefficients of x squared, of x, and our constants in the same way we did in the quadratic case. Well, now, if we do that, we're going to end up getting that negative a brackets alpha plus beta plus gamma is equal to b. Looking at the x squared term, looking at the x term, we're going to get a brackets alpha beta plus beta gamma plus gamma alpha is equal to c. And finally, we're going to get our negative a alpha beta gamma is equal to d. Again, we won't normally state them in this form. The form you'll normally see them in is dividing by negative a in this first one. The sum of the roots, alpha plus beta plus gamma, is equal, sorry about this, we're going to get that's equal to negative b over a. We're going to get that the sum of the product of each pair of roots. So we're taking, there's 3 possible pairs of the roots, alpha beta, beta gamma, and gamma alpha. The sum of those, again dividing by a this time, is equal to c over a. And finally, the product of the roots, alpha beta gamma, is equal to negative d over a. So same as with the quadratics, you're not going to get given these in your formula booklet, you want to know them off by heart. You might see these written sometimes as the sum of alpha is negative beta over A. This is a misuse of sigma notation, but it is used, so it's worth recognizing it. This is just a way of saying the sum of all the roots. And this actually matches up with what we had in the quadratic case up here, where we had the sum of the roots was also equal to negative b over A. And similarly, you might see this one written as the sum of alpha beta, which is saying the sum of the product of all the pairs is equal to C over A, which again is the same as what we had in the quadratic case, which only had one pair of roots in that case. And then finally, it would be overkill in this case, but the sum of all the triples would be equal to negative d over A. The only reason I'm writing that is because if you look at the quarter case, it's going to continue in the same way, and you will have various triples with your roots you can make, but the same relationship will stand. Okay, so we've got these complicated relationships. We need to make use of them. Let's see what sorts of questions we're going to need them for, and then let's see how we can actually go about using them. So the first example I want to look at here is for a quadratic equation. So the quadratic equation I want to look at, we're going to say we've got 2x squared, subtract x plus 3 equals 0. I'm going to tell you this has roots alpha and beta. And I want to find an equation with roots alpha plus 1 over alpha and beta plus 1 over beta. First thing to notice is, why can't we use the sort of substitution method we saw in the last video? Well, if you try using the substitution method, you're going to be doing that w is x plus 1 over x. And when you try and rearrange it as x, well, you're going to have to be using the quadratic equation or completing the square. It's going to be square roots all over the place. It's going to go terribly for you. So instead, let's work with these. I'm going to suggest we actually name these just so we can keep track. I'm going to let m be alpha plus 1 over alpha and n be beta plus 1 over beta, just so we can refer a bit more easily to the sum and the product of these roots. First thing I really want to do though here is let's note what we know already. Looking at the equation with roots alpha and beta, we can state that the sum of the roots, well, we know it's negative b over a. B in this case is negative 1, a is 2. So alpha plus beta is the negative of negative 1 over 2, or just positive half. And the product of the roots is c over a, which is 3 over 2. So get those down, because you're probably going to get marks for that, even if you go wrong later on. Getting that down makes it clear to the examiner you know what's going on. Don't just save it to use later on. So those are our old roots. We need to think about our new roots now, which I've called m and n. If we can find the sum and the product of these roots, we're going to be in business. So the sum of these roots is going to be alpha plus beta plus 1 over alpha plus 1 over beta. Some of this we already know. We've already said what this alpha plus beta is equal to. We've got it right up here. So we can make use of that and say, well, that's just a half. This 1 over alpha plus 1 over beta, not so easy to work with. What we need to do is make one fraction with them. So by making the common denominator of alpha beta, you're going to end up with alpha plus beta over alpha beta. Now we do know both of those because we've already stated above that alpha beta is equal to a half. And we've also stated above that alpha plus beta is equal to 3 over 2. So we're left just doing a half plus 1/3, and we're getting this is 5/6. So from our new equation, that's why I've fallen off the edge of the screen there. So from our new equation here, this is going to be equal to our new negative b over a. That's one relationship. The other thing we need to look for here is the product of our roots. So we need to look for what m times n is. So if we're doing that, we're doing alpha plus 1 over alpha multiplied by beta plus 1 over beta. And when we go through here, we're going to get alpha beta plus beta over alpha plus alpha over beta plus 1 over alpha beta. Some of these things we know already. We already know alpha beta because we already know that's 3 over 2. And if we already know that, we also know that 1 over alpha beta is the reciprocal of that. We know that's 2/3. The more complicated things are these two other fractions. Let's do the same trick again of making the common denominator. This is going to give us alpha squared plus beta squared over alpha beta. Now, that denominator, we know, but that numerator is looking a bit of a pain at the moment. We now need to use a trick. We need to think, how can we get something involving those? We could do alpha plus beta all squared, gives us alpha squared, gives us plus beta squared, but it also gives us plus 2 alpha beta. So let's take away 2 alpha beta, and now those two things are the same. Keep our denominator as it is, and now we can just work everything we know, because we know alpha plus beta is equal to a half, so we know that alpha plus beta squared is equal to a quarter. Minus 2 alpha beta is just going to give us minus 3 over alpha beta is 3 over 2, and now we can just whack that into our calculator or go through it if you want. We end up with 1/3 is equal to C over A. So now we have these two results, we've got to find values of A, B, and C which work. We might as well choose A to be a nice value, which is going to make stuff nice for the rest of us. If we write this one as 2/6 equals C over A, we can see letting A equal 6 will make life easy for us, and now we can just match up the rest. So if we do that, we're going to get B is -5, and we're going to get C equals 2, so our equation is just going to be 6x squared, subtract 5x plus 2 equals 0. Make sure you state your equals 0 when you're doing that. Okay, so that's the quadratic case. I'm going to give us a start on the cubic case, even though we might not go all the way through on this one. So on the cubic case here, I'm going to say we've got a cubic equation, x cubed minus x squared plus 2x plus 6 equals 0. And I'm going to tell you this has roots alpha, beta, and gamma. I want to find an equation with roots alpha squared, beta squared, and gamma squared. Now, if you looked at the last video, we did one where we could find roots with alpha squared, beta squared, and gamma squared with a substitution, and we had end up with square roots involved. But now we've got a cubic. If we have a square root involved, there's not going to be a nice way of isolating that and dealing with those. So that's not going to be a simple thing for us to work with. Instead, let's start by writing down what we know and think about what we'd want to work out. So one thing we know is that the sum of our roots, alpha plus beta plus gamma, is negative b over a, which is 1. The sum of our product pairs, alpha beta plus beta gamma plus gamma alpha, is going to be equal to c over a, which is 2. And finally, the product of our roots, alpha beta gamma, is going to be equal to -6. From there, we want to think about our new roots, which I'm going to call m, n, and p, just so I can write the sum of our roots here, and then I can say, well, I actually want to find alpha squared plus beta squared plus gamma squared. This is not obvious what to do now. We need to think we can get this by doing alpha plus beta plus gamma all squared, and at this point you might need to go away, do that expansion. You'll see that you get your alpha squared, you get your beta squared, you get your gamma squared, but you're going to end up with extra stuff you don't want. You're going to end up with an extra 2 loss of alpha beta plus beta gamma plus gamma alpha. And at this point, you can sub in everything you know. I'm not going to go through all the subbing in here, but you'll end up with -3, and that will end up tell you negative b over a. The next thing, you'd want the sum of your product pairs. So mp plus pm. Well, that's saying we want alpha squared beta squared plus beta squared gamma squared plus gamma squared alpha squared. And again, if you sub, it's not obvious how to get these. What could we square to get this? Well, we could square alpha beta plus beta gamma plus gamma alpha all squared. And again, go away, try this out. You'll get the bits you want, but you'll also get extra bits. The bits extra you'll be getting are subtract 2 alpha squared beta gamma, alpha beta squared gamma, and, I should put a plus there, and plus alpha beta gamma squared. At this stage, you might think we're still stuck because, okay, we know this first bit, that's going to be all good. But what do we do with this next bit? We can now factorize out alpha, beta, gamma. And if you do that, you're going to be left with alpha plus beta plus gamma. And we know that. And then we can work out that this gives us an answer of 16. The final one, the product of the roots, is going to be nice and easy for us, because that's just going to come out as alpha squared, beta squared, gamma squared, which is just a square of alpha, beta, gamma. So that gives us 36. I'll let you go through that more slowly by yourself to work that out, but hopefully that's given you the insight to do the harder Vieta relations problems.